All right, yeah, different from the timetable, I will not only talk about MaMBA, that will be about a third of my presentation, but also about what we're currently working on. Sustaining humans on Mars and planetary surface habitation. So like I said, I will talk about the MaMBA laboratory, but I will also talk about what is called the Humans on Mars initiative in Bremen. And my last point will be the Mars production facility. So we're not only staying on Mars, but we are also looking towards Earth and also looking not only at space engineering, but also production engineering. So first thing, the MaMBA laboratory. To give you a little bit of background, and I mean, Bill already did some work for me in his presentation by saying that the habitats that are currently existing, they're built for their specific purpose and they're really good for their purpose. But you could not take these habitats and place them on the moon or place them on Mars and you could survive in them. And I had exactly the same experience. So you can see before doing high seas for 1 year and Icarus 1, I was also at MDRS, so I've also seen some bases. And in particular, I spent 1 year at the high seas base. And maybe not every morning, but as an engineer waking up and seeing this part of the habitat and saying, yeah, on Mars this wouldn't work this way. And then that part of the habitat, no, that wouldn't work either. And then I started researching, maybe somewhere in the world there's a base that could actually be put on Mars. And I was a bit surprised to find out that's actually not the case. And so when I came back to Earth, I started a project that is called the Moon and Mars Base Analogue, where the focus is not so much to create a base where we can do simulations, but where the focus is to design it in the way that it could actually be placed on the Moon, on Mars, and would work. So our goal is not to, build it and construct it in a way that it could be sent off directly in a rocket, but to design the base so it's functional. And of course, we looked at the existing habitats and did some literature research, also looking at the actual bases, and tried to extract some lessons learned of the many good things that are already there, and also the things that needed improvement. And so it's a whole long paper. Just some of the examples to understand the direction we were thinking. One thing was to us it was very obvious that a Mars base should consist of several modules. I mean, it's nothing new. The ISS is built, assembled from several modules. But there are habitats that are just a single module. For example, the high sea space is mostly one module. Then one thing that was really great with the people that lived there was when a habitat had zoning, so you had some quiet areas versus some areas where there's lots of work and lots of noise. One of the common themes that we found in our literature research is that the other bases that didn't have this kind of zoning, all the crew members always complained about the lack of sound insulation. And so we said, okay, that's something we should take care of. Then from a scientific perspective, many of the existing bases either have no laboratory at all, or if they do have one, then it's equipped with some random science instruments. And if you're lucky enough to need exactly this piece of equipment that's there, good. But very often it's just a random collection of. So yeah, that's why we put it, there should be a usable laboratory. And the same is true for a workshop, because, I mean, most of you, if not all of you, have watched The Martian, so things will break. And things will need to be repaired. And for that, you need a workshop that's actually usable. And so yeah, I already mentioned sound insulation. And one thing I can attest from my personal experience, I mean, if you're in a base for a relatively short period of time, it's cool and exciting, and you're too busy to even think about other things than your work. But if you're there for several months at a time, it always looks the same. It's always the same colors, it's always the same furniture, it's always the same sounds, it's always the same smells. I mean, when someone is cooking, okay, one day it smells this way, then the next day it smells completely different because someone else is cooking, but then 2 months later you're just used to these smells. You can recognize whose cooking day it is by the smells in the habitat. Anyway, so there's a severe lack of sensory stimulation. And so what we are also trying to do for the MaMBA base is to take into account this this issue. And I mean, to some extent, there's nothing we can do about it. I mean, you are in this confined space. You only have so much you can take with you. But one component to fixing this issue or addressing this issue is by having the habitat in a flexible way, so you can rearrange pieces without having to assemble everything. So flexibility, adaptability. So I think in 2018, and Leszek was actually of great help to that. So we had our engineering experience and our engineering knowledge, and Leszek and some other architects helped us design a base that met most of the criteria that we set up for ourselves. So this is a layout of the MaMBA MaMBA habitat that you can see. You can see there are 6 modules. Each module has its main functionality. We made sure that from each module there's at least 2 exits to other modules. And then one thing, for example, where we deviated from the ISS, for example, and from I think all existing analog bases, we don't have 1 airlock, but we have 2 airlocks. Because if your door malfunctions, there's only one other way to get out, a second door. And then in 2019, we had a huge effort. In a couple of months, we started on the 31st of January with construction, officially with the construction, and then in late June, we had the very first test run, so that was a very short time frame, but we managed to set this up. And so the outer shell, but also the insides, the racks insides, and the scientific equipment, and the electrics and everything. And then we had I will get back to that in a minute, but we had our first test runs in, like I said, late June 2019, and then again in September. And the idea was that we invited scientists to conduct experiments the way they would be conducted on Mars. And they prepared their own protocols and conducted their own experiments, so that's where we made it easier for us. But what we were interested in was, we designed a laboratory. One of the 6 modules there is a laboratory. And the question for us was, we are engineers, we can design anything. And hopefully it works afterwards. But the question is, can someone who normally works in a laboratory, can they use this laboratory? Or is it too small? Is it too cumbersome to use the racks or anything? Or maybe the lighting is inadequate. And after the first test run, we had some lessons learned that we implemented for the second test run. But the overall result was that the scientists were very happy with using the laboratory. So very happy on that. To give you some impression on what the habitat could look like on the moon. So you see the several modules that are connected with each other. You see one of the two airlocks. And then one thing that is very important that also, the existing simulation habitats typically don't have a concept for radiation shielding. On Earth you don't need radiation, so that's fine. But if you are actually thinking about having a habitat on the moon or on Mars, you need some radiation shielding. And there are various options, various ways of doing that. And we said for our habitat, maybe not the easiest, but maybe one of the most efficient ways to do is to have a 3D printed or additively manufactured shield made from the material that's there in abundance. So a thick wall, essentially, or a big artificial cave made from the regolith that's existing. And different from this picture, the shield, of course, would be closing the entire habitat. And just if we did that for the image, you wouldn't actually see anything anymore. So again, you can see the layout, the 6 modules. I haven't mentioned, I said that they have their different functionalities, and we have one axis that is for work. It's on the right-hand side, from the airlock to airlock, and then on the left-hand side would be for leisure. So one sleeping module, one kitchen module, and one for relaxing. And then on the right-hand side, we would have the workshop, the laboratory module, and a place for exercising. And so some of the research highlights that we have done in the past couple of years. So one, I mean, we designed this habitat. In the meantime, so this is 2019. In the meantime, we've already found lots of things that we would improve. So maybe sometime in the near future, there will be a second paper describing the updated concept. We looked specifically, this is a fun thing. You know, the existing airlocks, actual airlocks, we don't really know what airlocks should look like on the moon or on Mars. Because if you look at the ISS, one, it's in microgravity, so the crew is moving differently. There is no dust, and there's no danger of any biological contamination. So actually, having an airlock in low Earth orbit is quite easy in a way. If you go to the moon or even on Mars, you don't have that luxury, and especially on Mars. So on the moon, the dust is just awful. I think we all know that. But on Mars, what often gets overlooked is that one of the reasons why we're going to Mars, I mean, there are many reasons to go, but one of the reasons from a scientific perspective why we want to go to Mars is to find out if there has been life on Mars. And if there has been, maybe it's still existing. And maybe there are some life forms that are still alive. And the thing is, I mean, we've just had Corona. I mean, one thing I know for sure is that if there is life on Mars, we don't want to bring it to Earth. And if we have a habitat on Mars, it will be, and there is life, actually living life forms on Mars, it will be a challenge to keep them out and to really make sure that we don't carry contamination from Mars to Earth. And like I said, there is no airlock that takes this issue into account so far. So this is one of the major issues that we ran into. What does the airlock need to look like? So another project that we did is the life support systems and infrastructure. So we did not set out to develop a life support system. I mean, there are other groups that are much better at that than we are. What we are interested in is the usability or the interface between the technical systems and the crew. So we constructed a small piece of a bioregenerative life support system, a photobioreactor, and looked into, you know, what does the photobioreactor need, but also what kind of sensor systems, how do you need to process the data and present it to the crew so they can grasp the important information very quickly. And then what does the crew need? I mean, everyone is talking about artificial intelligence, but do we actually trust systems that are artificially intelligent when they tell us, you know, press this button, do this, do that? You know, when your life support system is telling you the oxygen level is currently, I don't know, 15% and falling, and you're already stressed in such a base, and so your life support system is stressing you even more. Are you really trusting the artificial intelligence that tells you what to do? Very interesting question. And then one fun experiment we did is together with the German Space Operations Center. So we had a flight director who was supporting our were study participants. So they were operating on this photobioreactor, doing maintenance, doing repairs on this piece of equipment, and they had preset procedures and protocols that they were following very closely with the support from the GSOC, Space Operations Center. And we did this one for low Earth orbit, so for no time delay. We did this for 2-minute time delay, so that would be equivalent to transit to Mars, and we did it for 20-minute time delay. Actually, no, 10-minute time delay, but 20-minute both ways. And there are other people who have done this kind of study. But the way we did it is we prepared our procedures in a way that they were usable for this time delay. So we anticipated having a time delay. And so, for example, on the ISS, what you would often find is you have a procedure, the astronaut interrupts their work and then calls to the ground and asks, do I have the go to continue? And this kind of thing does not make sense on Mars. And that's a very easy, very obvious example. But that was the main point of these experiments, to really prepare the procedures so they would be usable under time delay. And it gets really interesting when we go into, maintenance. That something does not go as anticipated. So a brief impression from inside the MaMBA laboratory. It does not actually look like this anymore. This is from the time when we had the test runs with the scientists. One fun thing to note, well, fun, it was a lot of stress at the time. Initially, we thought, well, we can use the REX. We couldn't use the same REX system as they use on the ISS because it's already there. It's proven. The issue with these standard REX is they weigh more than 100 kilos, empty, and I think they're a meter wide, so they're massive. On the ISS, you can move them by just pushing with your finger. On Mars, you cannot. And so we said, well, we were already stressed with all the construction and everything, and one extra thing that came on top of our to-do list was design our own racks. And a small piece of, well, not really anecdote, but one piece of information. Design-wise, there's lots of room for improvement. But for example, the doors on the racks, they have little holes in them. And the reason why they have little holes is because otherwise you would have these walls of solid metal, which is super reflective and very annoying when you try to talk inside this small space. So I already talked about our first test runs. These are the two groups of scientists that we invited. So we had geologists, we had biologists, and we had material sciences. So we had these three foci. I talked about this. I see one piece of information for the photobioreactor. I've seen some people from the ÖVF. So this year for the MAD mission, we had not that photobioreactor, but kind of a downscaled version of it, or a simplified version of it, and had that in the mission, and had psychological experiments, human-computer, human-machine interaction experiments on this piece of equipment. And that will actually be presented at the ISC in Milano. I talked about that as well. So this is one of our test subjects working on the photobioreactor. And on the side, the small monitor is actually part of the communication system with the Columbus Control Center, or the German Space Operations Center. Okay. Done with MaMBA. Now, looking into the future, what are we doing now? So I already said humans on Mars. And humans on Mars is an idea that was born because the space people in Bremen were thinking, what could we do in the future, and also the material science, and which is quite a huge, not an institute, but a huge consortium, material sciences and process engineers. They were also thinking about what could we do in the future. What are major open issues that are in the future, but that we could work on, and also to understand the environment. The University of Bremen, well, generally Bremen is on the political spectrum is very far on the left, but the University of Bremen is the very first university in Germany that has sustainability as one of its guiding principles. And so, looking into the future, we said, okay, if we have, space flight is and human exploration. There's a lot of momentum. I don't need to tell you this. There's a lot of momentum. There's a lot of things going on. Everyone is pushing for the moon, later for Mars, and even beyond. But everyone is talking about how to get to Mars. And then when we think about how to actually stay on Mars and stay there for a long period of time and stay there in a sustainable way, then it gets more vague. So the setting that we are considering is we're looking into Mars, but not so much getting to Mars and Mars exploration, but more into settlements on Mars and really how to sustain them in a sustainable way. So of course, what we're looking at is supposed to affect the first missions, but the first missions are not our primary interest. But we're trying to look beyond, about at the point of time where the first settlements emerge. That's also why we're not interested in transportation, because if you're thinking that long term, that problem is already solved by then. And when you think about long-term sustaining humans on Mars in the long term and with minimal impact on the planet, one thing that I think everybody agrees on is that you have to use local resources to survive. That's, I think, out of the question. But the thing is, typically when people are talking about in situ resource utilization, they don't actually talk about resource utilization, but they talk about resource extraction, which is a huge issue. How do we get the water from the ground that's there? How do we get oxygen from the atmosphere? But they typically do not talk about the processing that needs to be done afterwards. So we actually had a lot of fun discussions with our production engineers. They laughed at us. And we said, there's a lot of iron on Mars. We just need to extract it. And they were like, okay, how are you going to do that? Well, there are some ideas. And then the next thing is, okay, what do you have then? You have some, let's say, some iron powder. What do you do with that? Well, we could make tools from that or spare parts. Okay, but how? Are you going to take your powder and place it on the surface on some desk, with the dusty environment? Where do you have the tools? If you're trying to process some surfaces, you always have some dust settling on it. Like I said, they had a lot of fun laughing at us. The good thing is we also got that in return, we also got to laugh at them at some of the naive ideas that they had. So really what we're trying to do is find ways to extract resources from the ground and from the atmosphere, and to process them into something useful, into something meaningful. So for example, spare parts. And this is where these 4 areas come into place. So production, like I said, you have the issue with the metal powder is not going to be pure. If you go into a production hall today, they always work with very pure materials. But also maybe they don't need to be pure. Just because today, when we buy, I don't know, an iPhone, it's very shiny and pretty, but do we actually need the back of the iPhone to be shiny and pretty? Probably not. But where's the boundary between, impure and a bit rough and still usable? For a rover wheel, for example, does it really need to be perfectly round if it's used on Mars, or can it be a bit, with some corners and edges? But it's a very interesting question. Where's the line? Where's the boundary? And obviously, if you're talking about having production on Mars, it's not like we have people in their spacesuit going into some production hall and doing some manufacturing there and working with tools there. It's also not going to be we have one giant production hall and it's pressurized with breathable air so that people have more dexterity. It's super resource intensive. So we believe that the answer is somewhere in the middle. So we assume that most of the production is going to be robotically, and humans only support both from inside the habitat, from some control room, and if there's the production line, let's say, is stuck in some way or the other, or a robot is stuck in one way or the other, then the humans really go outside and work on that. Which means that humans and robots really have to collaborate very, very closely. Much more closely than is done today. To give you an idea, we have, like I mentioned, we already have a lot of material science and engineering going on at the University of Bremen. So we have some small selection with the white frames, and we have received funding in 2021 from the state of Bremen to really push this topic forward. And we have received funding for 8 seed projects, total about 20 PhD students who are working on different aspects of this production problem. But the thing is, humans on Mars is not just about production and human and robots, but we're also looking into, let's say, human issues, into human behavioral issues. Because, for example, when you're supposed to go to or when there's something wrong in your production hall, how do you actually decide that you need some intervention? How do you decide when your spare part is actually good enough for using? So there's a lot of uncertainty. How can you make decisions under this lack of information? But also, what does this do with humans? So we have psychologists on our team, but we also have philosophers on our team. We have social scientists on our team who look into, how do we change? Well, one, here on Earth, how do we change? What does it do with us knowing that there are people on Mars? But also, what does it do to the humans on Mars being surrounded by this much technology, by being extremely dependent on this technology? What does this do with us? Yeah, we'll skip over this. The interesting, or maybe not. The challenge in a way is, so for Mars to really get production up and running, we have to deal with a lot of scarcity. So we have to deal with scarce resources. There's little water. There's even extracting, even though there is a lot of iron in the ground, it's distributed. It's in the ground and in the minerals. So we have scarce resources. We'll still have a small crew, maybe not as small as the very first crew to arrive on Mars, but it's still going to be very few people. So we have little workforce. We will have a lack of information, and there will be a lack of power. I mean, if you look at production today on Earth, it's power intensive. So it's extremely scarce. So when we are talking about production, and when we're talking about true in situ resource utilization, if you're talking about true utilization, we will have to deal with a lot of scarcity. And the thing is, that's where we're heading to today as well. I mean, we just had it about 2 years ago, less than 2 years ago, that Germany, not just Germany, but we had the feeling that we were running out of power because when Russia attacked Ukraine and wouldn't deliver gas to Germany anymore, so there was a hint of what we might be facing if we really have scarce power. our resources on Earth are limited as well. So we have, not as extreme as on Mars, but we have the same issues. We have limited resources on Earth as well. And this is really what we're trying to get at. I mean, one thing is we want to do production on Mars, but we also want to look at how can we do production on Earth. How would we have to change production on Earth to make it sustainable, to be able to deal with these scarce resources? So this is a mindset that we call the Martian mindset. And it's very much, putting together space engineering, production engineering, to maybe revolutionize is too big a word, but to really bring a new paradigm into engineering and to overthink. Overthink is not the correct word. To rethink how we're doing production, how we're wasting our resources today, and rather look into or understand that the resources that we have are limited, and to deal with limited and scarce resources. And for that, we submitted a large research proposal earlier this year. And the decision will be made next year, so there's still some patience required from our side. But even if this proposal, which will be quite, I mean, it's, like I said, it's quite a large thing, and it will can have a lot of impact. But even if it should get rejected, there will be smaller research proposals that will follow the idea. But yeah, keep your fingers crossed, please. And connected to this Martian mindset, I will now talk about the Mars production facility, where the idea is to build this idea, to build production the way it could be built on Mars. I mean, there are a lot of unknowns, there are a lot of question marks, but the idea is at the end to have a facility that has a production hall, have a habitat, or at least some sort of control room, and a way to switch between these two, and to really produce spare parts under conditions like they would be on Mars. Well, that's what I just said. And so this is what it would look like on as a floor plan. I don't have any. Well, actually, if you look at the background, if you ignore the white rectangle, you can sort of see it in the background. So you can see the habitat inside the shield. You can see the production hall, some other smaller parts. But functionally, what we will set up in Bremen is so we have the MaMBA module, which is already existing. We have a control room that's connected to it. So these are run under Earth conditions, just normal Earth atmosphere. And then, well, we have some airlock complex, let's call it that way. And we have the production hall where the conditions inside get increasingly Mars-like. And all the way at the end, because we have some process that will depend strongly on if there's, Earth atmosphere, if there's a Mars atmosphere, depending on the pressure, depending on if there's dust or not. So we will have vacuum chambers. And the good news is, for that we have already received funding, so we can start the project in January next year. So we're funded by the state of Bremen. And so we already have the funding for the facility to actually build and test our ideas. That's also why I'm saying even if the big research project does not go through, we can still do our smaller projects on it. And yeah, so if you're an engineer or you know someone who would be interested in helping us set this up, let us know or contact me. We can exchange details. One small aspect of this, and this might be also of interest for this community, one small aspect of this is that or maybe let me describe in more detail what we're doing. So yes, you see some, let's say, production stations. where the actual processing will be done, and then the materials will be transferred robotically. So most of the time, this thing will be either automated or run robotically. And then every time, not every time, when necessary something is stuck there or something is broken, then humans can transfer into this. And to make it realistic, our operators will not go inside the production hall, in normal clothes, but they will use breathing apparatuses. I wanted to run this facility under carbon dioxide atmosphere, but they wouldn't let me. So it's an atmosphere that's breathable. It doesn't kill anyone if you breathe it in, but the air is going to be extremely dry, and there might be some particles or some gases from the process unit. So people will go in there. Breathing apparatus, a suit. So if you have an idea for an affordable suit, also let me know. So coming back to the aspect that we're also trying to do is, we're talking about Mars. We're talking about a very long distance, and we're talking about a very long time frame. And I don't think I need to convince you guys that accidents will happen. And people working in this facility on Mars will not always be physically 100% fit and healthy. And so what we would like to do is, when we run tests in there, when we do psychological simulations studies, or when we do engineering studies, we would also like to do some tests with people with disabilities, physical disabilities. So again, if you're interested, contact me. Okay, this is some impression of what it might look like inside the production facility. So you have the rovers, you have the humans, workstations. To give you some idea of the scale, so you have the MaMBA habitat up there. It's actually hidden in the photo, on the left photo. This is the habitat. And the production facility would be covering most of the floor that right now is cluttered. It looks a lot cleaner and emptier already, so we're getting ready for the Mars production facility. Okay, I think I'm quite advanced in the time, so I will leave this as my last slide. And I thank you for your attention, and I'm ready to take your questions.
Thank you so much. And I think everybody's excited to ask so many questions because this is really lovely. Bill?
A great presentation, a lot of awesome work that you're doing. I had a couple of questions. First one on the MaMBA and the second one on humans on Mars. For the MaMBA concept, did you think through how those modules would be delivered and assembled together? Did you have a vision there?
Yep.
Great.
So one thing about the modules is you might have noticed that they're all the same. On the outside, they're all the same. And the size is also, so on the outside, it's, I think, 5 meters and a little bit. So the size is what we already have on the ISS. So it's something that has already been transported, at least to LEO. Mass-wise, I would assume that you could only get one of these modules in a rocket. And the connection would be with these small inflatables, also to save some room. Yeah. So these small little bubbles would be inflatables, which I assume could be grouped together. And then the interesting part is exactly the setting up on site, because I mean you can land with your rocket. Taking it out of the rocket is already a challenge, but then the thing is, you don't leave it where you landed. You have to transport it to the side, to your habitat side. And the way is, we looked into this with a team from robotics, and the idea is to have not one large robot, but really to have at least 5 robots working together. And so the the habitats or the modules would have some stiffening ring where you can place some anchor points so that you can grab them from below and lift them up. And then the 5, I mean, the number doesn't really matter, but your mini swarm of robots would have to transport it to the site. So it's it's a challenge, a robotics challenge. Nothing that I'm aware of that has been done so far. But the thing is, this is, to our knowledge, so far the best solution in terms of one, these relatively these modules have been built many times, so we know how to build them. We know how they work. They're relatively safe. So that's the plus point. And if you look at other ways of constructing a habitat, I mean, NASA recently had a habitat 3D printed, which is cool, which has a lot of advantages over having a pre-assembled habitat. But it has the main disadvantage, the huge disadvantage that you have to outfit the habitat on site. And here you can do the outfitting. So basically, you move the challenge from outfitting your habitat or your walls, essentially, your empty structure, to putting these together.
And kind of just to add on to that one, I didn't see solar arrays or radiators. Did you have a concept for power generation and heat rejection?
Solar, essentially.
Just the solar arrays would be somewhere?
Would have to be outside the radiation shield.
Right.
Obviously.
Right.
Yeah.
The other question, one of the challenges I had with 3D printing on ISS was the lack of quality assurance. So I had a part printed for the crew to have them use on the station in a procedure, and the NASA's quality assurance said, well, who's going to inspect the part to make sure that it was printed right, that it's ready to use, that it's safe to use? There wasn't like a delamination during the printing process and the thing was going to break. Fortunately, I wasn't asking the crew to do anything load-bearing. There wasn't a hazard in there that if it broke, it was going to hurt them. But that certainly could be the case. You're, like you said, relying on AI for answers. You're relying on a 3D printed part to be printed correctly.
Yeah.
So did you think through kind of that, in that manufacturing process, everything that we would do here on Earth, and mapping that to Mars, like quality assurance at the end when the part's manufactured? Did you think of solutions for that?
Yeah, I agree that is going to be an issue. In our mind, ideally, mission planners might have a different opinion on that, but ideally, from a habitat perspective, you would send the habitat parts, modules, to Mars before you send the crew. You assemble everything robotically, and then you do your tests. I mean, something like leakage tests, for example, making sure the power is properly connected and those things. Those can be done robotically or even in an automated manner. And this needs to be, in our opinion, should be done before the crew is even sent on their way to Mars. Because that's the only time where you can react to something not functioning properly. Beyond that, I mean, I'm sure that even when everything, all the tests, or the, let's say, technical tests are through, when the crew is moving in, they will still need to do some tests. I would also assume that, let's say, during the first days, they will probably remain in their lander, and only when they're absolutely sure that everything is working there. I mean, that's how I would do it. Like I said, we're not mission planners. There might be people who have a different opinion, but from a safety perspective, those are the steps that we would take in going into operation.
Yeah, makes sense. Thank you for a brilliant presentation. I'm a civil engineer and a material scientist, so I would be interested in the production facility, and I've already sent you an email, so we could get in touch later. And the questions that I have is, the first question is like, what's the timeline for the production facility? And second question is, when you say sustainability in Mars, so do you mean longevity of materials so that when the resources are scarce, they can be reused for a longer period? Or what exactly do you mean by sustainability there?
Those were several questions. So the timescale for the production facility for setting it up is 3 years. And then also doing a stepwise, going into operation one step after the other. But that's pretty much the time frame. And also we have to spend the money, I think, by 2029. So there's not much room for delay. We have 1 year buffer. But yeah, it's realistic. I mean, we have already contacted some potential manufacturers, so it's not like we would start from scratch. For this research project, it would start earliest. No, not earliest. It would start in January 2026, and would be running for 7 years. Potentially being extended beyond that, but that would be the first funding phase, 7 years. The other question was sustainability. So when we talk about sustainability, we mean mostly sustainability on Earth, but we do think about sustainability on Earth because you raise an important question. I mean, at the moment, our focus is, just getting the resources from the ground somehow, and being able to process them in a way we can have anything that works. We will leave that to the second funding phase, but it is an issue. I fully agree. I mean, it's one thing to extract these resources, but we could also take the spare parts or whatever we have manufactured and disassemble it and reuse those resources to really go full circle back into our production process. And we do, for example, in the process that we are considering, we have already excluded those that would mix these different materials in a way that they could not be, taken apart anymore.
Okay, thank you very much.
But we're not doing full circularity at the moment. We're, getting started.
Hey, Christiane, it's Florian. Congratulations to the extreme scale and broadness of your approach. I so far have only seen individual of your experiments or met them at the expeditions we do. So to see the entire scope is really impressive, and also good luck on spending all the money that you hopefully will get.
We might have some more experiments for the future for you.
I mean, I have a whole list of notes that I just want to comment on, or ask for more of you. But I think Bill's comment on quality assurance is a really, really well and really good point. Also which procedures, which standards you would establish, which devices and tools you would have to bring to Mars to actually do your own Q&A, to set parameters that are acceptable for the type of manufacturing you have available, and then to give at least a baseline of assurance and say, okay, we're going to use this part 10 times most, so we can get away with this much of flex or this much of resistance or whatever. This is then the standards you would define, but to have also the crew trained in Q&A, sort of doing their own QA on site is a really interesting concept to go down on.
Yeah, and for as a comment to that, for the production, we are actually thinking exactly in that direction. What do we need to monitor? How do we need to monitor? Because, like I said, you cannot just take your random materials that you extracted from the ground, but you have to make sure that whatever you're producing is having the properties that you need, meeting the minimum requirements of what you need. It's not. I mean, it's related to quality assurance. It's not quality assurance as such, but we're definitely going in that direction as well.
Exactly, and then thinking about industry as a economical branch in a broader scale, I think is also quite interesting because they have for several reasons implemented strategies and procedures actually that are, I think, somewhat relatable to this field. There's incident reporting on a really highly imprecise way. There are also non-accidents that are reported that are considered by safety officers and stuff like that. So this also would kind of get into this topic. Then again, manual labor, taking care of your fingers. It's, I think, something that is not that dangerous right now on the station, like smashing your thumb with a hammer or stuff like that. But I think once you get into manual labor, this is the first thing you're going to damage is your fingers, and that's actually the most important tool that we have astronauts up there. So I think also this connection already to the para world, I think, is really valid. And thinking about things like a media blasting cabinet, where you already have this Mars environment in a box, and then the clean world outside. So I think this would also kind of be a nice analog.
And the hurdle to even go to your production line and risk not even your fingers. I mean, if on Mars, if you damage your gloves, you might risk even more than your fingers. So the hurdle to even go to your production line is much higher than it would be on Earth. So for production, I mean, to think a couple of steps ahead, we're talking about floor shop workers working in home office, essentially.
Exactly, but at some point you might need to get in there, and then like, what is the interface? What is the barrier? What is like, how close can they get? Like, where will the robots be when the humans come in? Do they all move away? But essentially, like modern industry basically looks like this. Like if you visit a modern production hall, there's little humans there. If you visit a modern metal smelting hall, there's like no humans. They're just in the control room. Already we have kind of this standard established somewhat in industry. Of course,
they don't work entirely without humans.
Exactly, but like the general thing is like, if you compare modern industry to industry like 50 years ago or 30 years ago even. And like the last thing I wanted to point out, and then I will shut up forever, is in MRD 18...
Please not forever.
In MRD 18, we already had, and I'm slowing down for the interpreter, sorry. In MRD 18, actually, Michael Müller and Sophie Gruber ran the ADAPT experiment that kind of went through all the steps that also Bill outlined there. So we had a device like a scoop, break accidentally, and then did the entire kind of procedure of reporting the damage back to Earth, waiting for them to send the 3D file, printing the file on site, reassembling the tool, testing it again in the environment, and verifying that it works. Of course, it was successful, but in the end, to verifying that all the steps are kind of displayed or kind of dargestellt, like reflected in the procedures. And like also like working through the entire thing basically was kind of something that's sort of related to where this is going. So I think it's a really interesting point, and good luck with that.
I think we need to give you a second slot because
Well, I will be here until Monday, so...
Another excuse for you guys to stay longer. This question.
I wanted to come back to the question of safety, and I was wondering how you're handling fire safety in such a habitat. What are protocols that you would follow if a fire actually breaks out? If it's possible to like disconnect certain rooms to deplete them of oxygen, or is it possible to make like a panic room? What are the plans on this? For example, here, if I look at this, is it possible to disconnect like one part where a fire broke out? Because for me, that would be like a big problem if a fire breaks out, especially in an environment where you don't know how the fire will behave and you cannot just easily see it too.
Yep. Fire is actually was one of the reasons why we have these different modules. Because, for example, if you look at the high seas habitat, it's one big dome essentially. If you have a fire breakout in that habitat, the crew goes outside. If you have that on Mars, there's nowhere you can go. You lose your entire habitat, and that's exactly the reason why we said we have to have different modules where you can at least close some hatch between them. So these doors essentially between the inflatable connection modules and the actual modules, they can be closed pressure tight. As to disconnecting, that's not so trivial. As in, disconnect in the way that you can shut them off and you can depressurize one module entirely. That's relatively easy to do. But to really move them apart, that's more tricky. And that's one of the things that we learned from experiments. Well, not on the space station, because we can't do fire experiments there, but on some of the Cygnus capsules that return to, well, not return, but they go into the Earth atmosphere and burn up with all the trash inside, and there you can do fire experiments. And one of the things that we learned there, and by we I mean colleagues at the ZARM who work on fire safety. One of the things we learned is that fire in microgravity, but also in reduced gravity, is behaving much, much differently than on Earth. One thing that many people know is the candle flame. So on Earth you have something like this, and then in space you have basically a sphere. So that's the easy part. The interesting part is, one, in microgravity you have materials that are flammable that are not flammable on Earth, which is an issue. But also the direction of flame propagation is opposite to what you would expect on Earth. On Earth, if you blow at a fire, it moves away. The flames move away from you. In microgravity, if you blow at the fire, the flame comes towards you, towards the supply of oxygen. So we don't fully know yet what will happen on Mars. Roughly 1/3 of 1G. But yeah, fire and habitats. I think it's a whole huge issue in itself. So in terms of what we can do from the habitat side, at the moment we cannot even give recommendations for the materials to use. Because like I said, they behave, like some things are flammable in space that are not flammable on Earth. So we can only look into procedures and into ways of keeping the crew safe and providing not one single module that is, like a bunker, but to make sure if any of these modules fail, you can evacuate to any of the other modules. So that's why there's 2 exits to each module. That's also why the way the functions are distributed, the main functions, they're all on the ground floor. Also helps if there's some injury and you have trouble getting upstairs. Would be a bit annoying if the toilets were upstairs and you broke your foot. What else do we have? For example, for getting from the upper story to the lower story, it's a bit difficult to see in this image, but there's this black line, this vertical black line going all the way through. So that's I don't know what it's called in English, like a fire pole. So you can just, like the firefighters, you can just slide down. And honestly, I would probably rather use the fire pole even without a fire than the stairs. But so that would be the fastest way to get down if there's a fire. And then let's say if you lose your kitchen module, well, it will be annoying, but the crew lives. One of the things that we learned during Icarus 1 is you have to distribute your supplies. It's a very bad idea to have all your kitchen supplies in one module. It's a very bad idea to have all your spacesuits in one airlock. It's and so on. So you have to distribute your supplies anyways. And that's our way to tackle the fire issue, because it can't really, even if we do more research, I'm sure we cannot eliminate fire hazards to 100%. But rather the approach should be to be prepared that there will be a fire.
And how would the detection of the fire be handled?
So on the ISS today, they have smoke detectors. My colleagues told me that they do occasionally give false alarms. And the few times that there was a real fire, they did not trigger an alarm. So I'm pretty sure there will be smoke detectors on Mars. They might work differently than smoke detectors on Earth, I hope. The question, one question is like, what kind of chemicals are even generated, because reactions occur differently. But it will be very difficult to really. I would say it's even worse than with the AI. I don't think that the smoke detectors can and will be trusted. So yeah, it's an issue. We actually had a lot of debate about what could you really ensure the safe operation of a base if you have something like a schedule where the crew, there's a time when all crew members are sleeping, or should we have a shift schedule, which would be horrible for crew dynamics. So, yeah. I mean, one way to help with that, it's not really a solution, but it can be part of a solution, is to not only look at smoke, but I mean, there will be cameras everywhere anyways. So have infrared cameras, so you can see where you have fire or smoldering, and also the temperatures are going to, in microgravity they can be much higher than they are on Earth. So less, I think it's less smoke that's generated, but generally the temperatures can be higher in fires. And so unless the fire is somewhere hidden, that might also be a way to detect them. But yeah, it will be. It will not be easy. And then also, when you think about the NASA, there's talk about having an atmosphere on the moon with more oxygen than we have here on Earth, which makes it all the more unpredictable. But it makes it more predictable, or it makes it predictable that there will be a larger fire hazard. So, yeah, fire will be an issue.
So I'm going to call fire. Not that it's one, because it's so interesting. And I think next time in the conference we're going to make 1 week long and 5 hours each, okay? Good luck for you guys, by the way. Thank you so much for this wonderful talk.